Okay, so we'll be looking at something new in mechanics. We're going to be looking at moments. And a moment is the turning effect that a force applies to a body. So here I have a pivot point P. I have a force of 20 newtons. To calculate the moment, I need to know the distance, the perpendicular distance from that pivot point to the force. And I just need to multiply these two values, the force and the distance, and the unit is going to be a combination of newtons and meters. The distance we use must always be the perpendicular distance. So sometimes we might need to extend the line of action of the force to make sure we can have a perpendicular approach to the pivot line. So extend, draw your perpendicular distance, and once again, it's going to be the force and the distance multiplied. The notation I'm using here just denotes that the moments are being taken around the pivot point P. Be careful to include the direction that the moment is turning. So that's either going to be clockwise or anti-clockwise. We don't want to see right or left. We don't want to see up or down. It is a rotation, it's a turn, so it should be clockwise or anti-clockwise. Okay, one more to consider. If the line of action for the force actually goes through the pivot point, there will not be any moment. There is no turning effect if the line of action is going through the pivot point. It's not making any turn happen, and you can think of that when we use the between the line of action, the force, and the pivot point. So the moment is just zero. Okay, so another consideration when trying to calculate moments is that you may be given a distance that is not the perpendicular distance, and that may be accompanied by an angle. We should be able to get an expression for the perpendicular distance, the one that we want. And we can do that by using trigonometry, basic trigonometry, SOHCAHTOA. So here we have the opposite, which lets me be using the sine function. And I can say that the sine of 30 should equal x over 2. And I get x equals 2 sine 30. Now that I have an expression for that perpendicular distance, I can add element as usual. So it's the perpendicular distance by the force, so multiplied by 10. Gives 20 sine 30, which cancels down to 10 meters. So the moment here is 10 Newton meters. Okay, so let's look at one more case where the distance that we know is not perpendicular. So this diagonal distance is 3 meters. I'll put the angle over here this time. Let's make the angle 65 degrees. Okay, so how do we find this perpendicular distance x? Well, there is a general result for the perpendicular distance in this case, and it will be the hypotenuse, the trig ratio, and then the angle size. So in this case, 3 cosine 65 will give me that perpendicular distance. In the previous question, it's the hypotenuse, the sine function, 30 degrees, 2 sine 30. So you can actually quickly get an expression for the perpendicular distance when working with moments. So let's go ahead and find the full moment. It's that perpendicular distance multiplied by the force, and that gives us 15 cosine 65, and to a couple of decimal places, 6.539 Newton meters, and direction anti-clockwise. Okay, so getting into some examples that you'll have in front of you. In question A, we're just asked to find the moment of the 6 Newton force. It's going to be the distance multiplied by the force, 18 Newton meters anti-clockwise. All right, in part B, we can see we're going to be moving anti-clockwise. And if we use the standard result, the standard format for the perpendicular distance, that will give us 8 sine 35. And we'll multiply that by the 12, work that through. and we get 55.06 Newton meters in a clockwise direction. Okay, in this question, we're asked to find what each of the forces, or we're asked to find the moment that each of these forces will produce. For the 5 Newton force, quite straightforward, gives us 10 Newton meters. And for the 8 Newton force, once again, using that standard format for the perpendicular distance, it's going to be 2 sine 50 multiplied by our 8 meters. And this one's going to be anti-clockwise. So altogether, 12.257 Newton meters anti-clockwise. Okay, looking at this example, we realize that we can't exactly have clockwise and anti-clockwise movement at the same time. One of them has to win out over the other. And in the next video, we'll be looking at resultant moments and how do we calculate which direction wins out over the other.